In order to understand periodic trends, we need to understand this idea of shielding. Now, we've talked about shielding some, we just haven't just explicitly defined it yet. So, shielding is also known as your screening effect. It's the reduction in the nuclear charge experienced by an electron due to the presence of other electrons. So, we've got what we call your effective nuclear charge. Your Z effective is your Z actual. Z is the number of protons you have in your nucleus minus the shielding of those electrons are experiencing. So to be able to predict periodic trends, we need to consider two things. We need to consider not only electric configuration, but nuclear charge and the actual effective charge of the number of protons in the nucleus. So what is shielding? Well, shielding is, remember, all of your protons and neutrons reside in your nucleus. So the atom's nucleus is very, very dense. That's where all the weight is in the nucleus. Protons and neutrons are what add mass to the atom itself. So the nucleus is very, very dense. The volume of the atom is mostly empty space. It's made up where your electrons are. But again, the electrons are moving constantly. They're making the orbits, they're orbiting around that nucleus. Okay. And we know based on probability where we might be able to find one. All of those ideas coming into play. Well, so the electrons have allowable energy levels they're in. You've got your n equals 1 energy shell that's closest to your nucleus, and then n equals infinity, which is furthest away. The electrons, the further away they are from the nucleus, the less they feel the pull of that nucleus. Because one, they're distance-wise, they're further away, but two, there's electrons that are repelling them, that are blocking they're blocking them from that full effective nuclear charge. So even if I say, like, let's say I've got fluorine, and I know fluorine has 9 protons and 9 electrons. It doesn't mean that each electron feels the full pull of one proton because there's electrons in the way. The electrons that are closest to the nucleus feel the strongest attraction. These electrons, though, are repelling what we call your outer electrons. So the further you are from the nucleus, the more that electron is being repelled. This needs to be taken into account when we're thinking about what the trends are that we're going to be talking about, which is size, atomic and ionic, ionization energy, electron affinity, metallic character, etc. It's a lot of the trends we're going to see on the table. So, effective nuclear charge. Electrons are simultaneously attracted to the nucleus, but also repelled by one another. Other electrons are shielded from the full strength of the nucleus. And this is again called your shielding effect. So the electrons, let me back up one slide quick. The electrons here that are like next to each other, they do repel each other a little bit, but not as much as the ones that are full blocking another electron. The repulsion here is a lot stronger than the repulsion here. Okay. So outer electrons are shielded from the full strength of the nucleus. Again, that's called your shielding effect. And it leads to your effective nuclear charge. The effective nuclear charge is the net positive charge that's attracting an electron. Valence electrons, again, valence are further away from the nucleus, the core are the ones that are closer in. A valence electron feels less than the full positive charge from the protons in the nucleus. It only feels the effective nuclear charge. Electrons in the same valence shell shield each other very little. So again, that's what I'm talking about here. The same valence shell shield each other very little. Well, most of the shielding comes from the inner core electrons. So this shielding here is a lot more effective than next to each other. So what are your periodic trends? So the big pair of trends we're going to talk about are atomic and ionic size. And we will talk about these specifically within them. We'll be able to describe them based on the periodic table and all of that. But your atomic size increases as I go across the table and as I go down that table. So size increases going from right to left and going top to bottom. Ionization energy, we will define this when we get to that chapter, but energy required to remove an electron from an atom or an ion, generally speaking, increases across, left to right, and up the table, bottom to top. But there are important exceptions, and you need to be able to predict these. Electron affinity is the um, energy released, really, when electron is added. So Ionization energy required for removing an electron. Electron affinity is energy release because we're adding an electron. So the energy release when an electron is added to an atom or an ion. Generally speaking, goes across the table like this, but there are some really important exceptions here as well.